myself, Dr. Mohammed Ibrahim, Assistant Professor in the Department of EEE, KPR Institute of Engineering and Technology, Coimbatore. So we are going to discuss about the Ferranti effect. So what is called as an Ferranti effect and where it occurs in a transmission line? So generally the Ferranti effect occurs in a long transmission line at the receiving end area. Okay, so there are different types of transmission lines are there. One is called as a short transmission line, a medium transmission line, and then long transmission line. As the effect of Ferranti is happening in an long transmission line, so the receiving end voltage would be higher than that of an sending end voltage. So this happens due to an lightly loaded condition or an unloaded transmission lines. So what may causes this rise in voltage in the receiving end area? So it is happening due to the line capacitance and an lightly loaded condition or an unloaded condition. So as of line capacitance is concerned, so the significant capacitance in the long transmission line, so combined with an inductance causes voltage rise in the receiving end area. So the next effect or the causes is by means of a lightly loaded condition or an unloaded condition. So what may be the effects of the rise in receiving end voltage? The voltage rises in the receiving end, which can cause the over voltage condition and potentially damage the connected equipments, and parallelly it causes an power quality issues by affecting the stability and reliability of the power system too. So how we can able to mitigate these issues? So by means of adding a shunt reactor and a series capacitor in a transmission line. So today we are going to discuss how the Ferranti effect can be discussed with the help of a software called as an ETAP. So I have discussed within 3 different transmission lines, short, medium and long. So based upon the distance it has been classified. The first circuit, the first network shown is called as a short transmission line. The second one is based upon the medium transmission line, and the third and fourth diagram deals with the long transmission line. So I have taken different sets such as an 11 kV transmission line, 110 kV transmission line and 765 kV transmission line. Okay, so you can able to see the length of the transmission line is 1 kilometer, 50 kilometer, 150 kilometer and 3 kilometers of 300 kilometers length of line. When we have an load flow analysis here, so we can able to see so how will be the sending in voltage and then receiving in voltage. So you can able to see here, so this is called as an sending in voltage nearer to the grid, and this is called as a receiving in voltage. Well, in case of a short and medium transmission line, so it is maintaining with an nominal bus voltages of 100%, while in case of a long transmission line, so 150 kilometer length of line, it's rising of nearly 1.3%, while in case of increase in length of line, it is increased by means of 105.5%, that is nearly 5.5% has been increased from the nominal bus voltage. And this is the same condition in case of an 110 kV of transmission line, and similarly of an 765 kV of transmission line. So when there is a length of line is less, so the charging capacitance is also less, so there we won't be considered theoretically in case of a short and medium transmission line. In case of a long transmission line we have to consider. So why you have to consider? So there is an effect. So there is a rise in voltage is happening, so we have to consider the capacitance effect in case of a long transmission line. Okay, so what we have discussed is called as an how we can mitigate this issue, right? So the same 300 kV line has been taken here. So there are 2 methods, so we can able to reduce the rise in voltage by means of a shunt reactor and then series capacitor, what we have discussed. So here I have given a shunt capacitor to stabilize a bus voltage, that is receiving in voltage. So the nominal we have received then 300 kilometer of length of line is about 105.5%. By adding the shunt reactor factor. So there are in ETAP we have two different types of loads are there. One is called as a static load, another one is called as an lumped load. So I have used a static load with an less than 1% of power factor, so it can act as a shunt reactor, so which consumes the reactive power. So as of conception is happened, the voltage has been reduced to 100.4 from 105.5 percentage. So this is one of the method how we can able to control the bus voltage. Okay, so how the voltage has been rising, so we have shown, so by means of an lightly load or low load condition. So the same 300 kilometer length of line has been taken with an 105.5 percentage of loading condition. So when we have a lightly load of 10 MVA and this is a nominal load of 420 MVA for this network, so if you consider lightly loaded condition, there is an increase in bus voltage is happening at the receiving end area. Even the sending is maintaining at 100 percentage, receiving is rising within a charging capacitance then 105.4 percentage, while in case of a nominal load, so the voltage is maintained within 100 percentage. So if there is an, so this is what so what we are going to the inference from this diagram is, so we have to maintain a nominal load in a network. Okay, so if there is an increase in load, so there would be an decrease in voltage in the receiving end area. So how we can able to maintain this bus voltage? So by means of an adding in capacitor banks. So this is an example. So I have added an 100 mVAR capacitor, so and there is a rise in voltage from 97.69 to 99.81 percentage. So this software may helps to see the real time of how the voltage has deviation in the receiving and sending end area, and how the low or lightly loaded conditions of a transmission line, how we can able to mitigate the highest voltage by means of a shunt capacitor, and how we can able to have an where we have to have a capacitor bank. So these are some discussions which I have interested to discuss with you all. So kindly have and share with your friends to know all those things what is happening practically. Okay, so understanding and addressing the Ferranti effect is crucial for maintaining the stability and reliability of the power systems. Thank you all for the patience listening.